Okay, hi, so in this video we're going to speak about measuring waves. So in the last video we discussed what a wave is and the different types, but they're no use to us if we don't measure how much information is being carried by them, how much energy is being carried by the waves, and so we need to be able to do that. Now, if we take a generic wave that will look something like this. Okay, so this is meant to be symmetrical. I've done a fairly bad job of making it symmetrical, but just pretend that it is. Now, what we have are different features of this wave. So, the top of a wave, let's say right here, this is known as the crest, or the peak. So, crest or peak. Okay, and the bottom of a wave, you can call that a peak if you want, but often we distinguish between them by calling it a trough. So you've got peaks or crests and troughs. Now, normally you'll see an imaginary line drawn right through the middle of the wave. Might look something like this. Okay, and this is just to show that the wave will go above the line and then below the line, and then above the line and then below the line. Okay, so it's an oscillation or a vibration. Now, one complete wave is from a point, let's just take it at the peak, to the peak again. This here is a complete wave. So if we cut this off from everything else, this would be one complete wave because it started at a point, it's oscillated, it's gone down to the bottom, and then it's come back up. And look, now it's back where it started. When that happens, that is a complete wave, okay? Now, the physical distance between here is known as the wavelength. So this is the wavelength. And often you'll see that given the symbol lambda. Okay, I'll draw that a bit bigger up here. Lambda looks like that. Okay, and that is used to denote wavelength. Now, lastly, what we have is this distance here. So from the baseline to the top or the bottom, because it should be the same distance. So this should be the same distance. This distance from the middle to the top or the bottom of the wave is known as the amplitude. Amplitude. Okay, and the greater the amplitude, the more energy which is carried in the wave. So a higher amplitude means more energy carried in the wave. Okay, so we've got the peaks, the troughs, the wavelength, which is the distance between 2 points on the wave. So after one complete wave, that would be the wavelength, how far it's travelled. This is a physical distance. You can measure this in meters, or centimeters, or micrometers, or whatever. Depends how big the wave is, okay? But the wavelength will be measured, and it's a physical distance. And then also we have the amplitude. Right, now that would be fine if the wave just sat there and stood still, but it doesn't do that. The wave is always moving, and so we have more properties of the waves. The first one is the frequency. Now, you will have heard this expression, especially with radio, so radio frequencies, and that's actually because radio waves are electromagnetic waves, and this is a property of waves. Now, the frequency is defined as the number of wave crests or peaks, so number of crests that pass a point every second. Okay, so for example, if we had this barrier here, right, the wave is going to be moving in this direction. And let's say that this peak, okay, passes here, and these four other peaks also pass that barrier in 1 second. Those four peaks passing that barrier mean that you have a frequency of 4. And the unit of frequency is hertz. Hertz. So if there were 4 wave crests passing the point in 1 second, that wave would have a frequency of 4 hertz. Okay, so now if we think about it, what's going to affect how many times a wave will pass a point? Well, it depends how fast the wave is moving and how far the distance is between one crest to the next one. Because if the crests are miles apart, even if the wave's moving fast, the frequency might be quite low. But if the waves are really, really close together, then the wave, if it's moving fast, loads and loads of crests are going to pass the point. So the frequency also depends on the speed and the wavelength. And so we have this equation. We have wave speed, sometimes we denote that v for velocity, is equal to the frequency, just f, times by the wavelength. If you remember, we denoted that with this letter lambda. Now the important thing here is that we have to make the units match. So for example, if we are doing speed in meters per second, let's say meters per second, that means the frequency, hertz is absolutely fine because hertz is per second, so that's this part done. But that means the wavelength we have to do in meters, okay? This meters and this meters have to match. So if we were doing the speed in kilometers per second, we would have to do hertz, and also we'd have to do the wavelength in kilometers. These units have to always match. So be careful, that is a trick that sometimes examiners will play. But let's do a quick example now. Let's say that a wave, okay, has a speed, so speed of 20 meters per second, okay? That's how fast it's moving, 20 meters per second. And the wavelength, so lambda, is equal to, let's say 10 meters, okay? Let's work out the frequency. So pause the video now and try and have a go yourself. Okay, so I hope you had a go. Basically, we're just going to sub this into the equation. So V equals F lambda, or F times lambda. That means that 20 is equal to, well, the frequency is what we're trying to find, and that is times by 10. So 20 equals, let's move this down a bit, 20 is equal to 10 lots of the frequency. We're going to divide both sides by 10. Divide both sides by 10, like so. And that means that we get 1F on this side, because 10F divided by 10 is 1F. And 20 divided by 10 will give us an answer of 2. So the frequency is equal to 2 hertz. Okay, that was a simple one, but that makes sense, because if it's moving 20 meters every second, and the wavelength is only 10 meters, it can do that twice in a second. And so the frequency will be 2. Okay, so I'll give you one more example to do yourself, and then we will call it a day for this video. So let's say we had a wave, okay? So we've got a wave, and the frequency is equal to 150 hertz. Okay, now the speed of the wave is equal to 30 meters per second. Okay, what I want to know is the wavelength of this wave. So pause now and have a go. Okay, I hope that went well. So we're just going to sub into the equation again. V equals F lambda, which means that 30 is equal to 150 times by lambda. What we need to do to get lambda on its own is divide both sides by the frequency, which is 150. So we're going to divide this by 150, and that means that we'll have lambda on this side, and this will be 30 over 150. Now what is 30 over 150? Well, that actually cancels down to 1/5, or 0.2. And so 0.2 equals lambda, and that is 0.2 meters. 0.2 meters is the same as 20 centimeters. Okay, so the same thing there. I could write it in meters, or I could write it in centimeters. It's up to you. Okay, so I hope that's made sense. I'm going to wrap up there because that was quite a lot of information. But make sure that you do know all of these different features of waves. You need to know what the frequency is, what the wavelength is. You need to know what the amplitude is. And so if you do have any questions on that though, then please do feel free to give me an email using the link below, or comment in the box below and I'll be sure to get back to you. But I look forward to seeing you in the next video.